Hello everyone, and welcome to IP Tech Talk. Today, we're going to talk about wired and wireless convergence. As discussed in an earlier video, wireless networks were initially used as an extension and supplement to wired networks. But due to the rapid development of wireless networks, many organizations now have started to deploy fully wireless campus networks at scale. Clearly, wireless networks have switched from a supporting role to a leading role. So, how do wireless networks achieve such a radical change? That's the question I'll be trying to answer in this video. Generally speaking, wireless networks on campuses have gone through 4 distinct phases of evolution. In the first phase, wireless networks serve as an extension to wired networks. At this phase, FAT APs, a typical component of wireless networks, are deployed at the end of wired networks. As you can see in this figure, FAT APs are directly connected to access switches, and they emit radio signals through which wireless terminals access the network. The FAT APs are also responsible for wireless service configuration and management. So you can see that at this phase, wireless networks further extend the reach of wired networks. You may wonder, why are such APs called FAT APs? The reason is because FAT APs have powerful functionality. In fact, FAT APs can not only emit radio signals, but also independently implement management and control functions such as security encryption, user authentication, and user management. We can easily find FAT APs in our everyday lives. For example, our home wireless routers are typical FAT APs. Using such routers, we can set a password for the home Wi-Fi network, configure a blacklist or whitelist to control user access, and perform other tasks. So, we can use Wi-Fi and FAT AP built wireless networks in a similar way to our Wi-Fi at home. Next, let's move on to the second phase, in which wireless and wired networks work independently and separately. At this phase, the coverage of wireless networks gradually expands, extending from home networks to enterprise networks, and even large public places, where users access the network through Wi-Fi. In this case, many FAT APs need to be deployed. Each FAT AP, however, is independent and autonomous, without any centralized management and control device. This makes it difficult to manage them. To solve this problem, mainstream vendors in the industry proposed a WAC plus FIT AP architecture. This new architecture replaces the original FAT AP with 2 new types of devices, which are WAC, short for Wireless Access Controller, and FIT AP. FIT APs provide less functionality than FAT APs, because they provide only radio signals without the management and control functions. Instead, the management and control functions are migrated to the independent WAC, which uses the CAP-WAP protocol to centrally configure and manage all FIT APs. This means that the basic functions of wireless networks can be implemented using WAC plus FIT APs. Usually, the WAC is connected to a core or aggregation switch in off-path mode, but in some cases, the WAC can be deployed directly between FIT APs and the core or aggregation switch. FIT APs are connected to access switches. At this phase, data traffic and configuration management of wireless networks is performed separately on the independent WAC, whereas that of wired networks is implemented independently on switches. So, wired and wireless networks actually work independently and separately. Now, let's talk about the third phase, in which wireless and wired networks are seemingly converged. You will understand shortly what I mean by seemingly. As I just mentioned, in a WAC plus FIT AP architecture, wireless and wired networks coexist and work independently from each other, and they have to be configured and managed separately. This, however, complicates management and increases deployment costs. So is there a way to integrate wired and wireless networks into one network for unified management? In search for an answer to this, numerous industry vendors started putting forward their own wired and wireless integration solutions. As you can see in this figure, wired and wireless integration means that the switch for wired services and the WAC for wireless services are integrated into one device for unified management. Huawei's ACU2 card solution is an example of wired and wireless integration. The ACU2 card is a value-added service card installed on a switch that can process wireless services. Simply by installing such a card, a wireless network can be overlaid on the wired network to provide wireless access capabilities. This implements wired and wireless integration and simplifies device management. At this phase, wired and wireless networks are gradually integrated by using value-added cards. However, this still falls far short of a truly converged wired and wireless network. As you can see in this figure, although wired and wireless networks are seemingly converged, wired and wireless data traffic is still processed separately, with wired traffic processed by the switch and wireless traffic handled by the ACU2 card on the switch. That's why we call this a seemingly converged wireless and wired networks model. This model is like a couple who seem to others as happily married, whereas in truth, they're more like friends. Finally, let's take a look at the fourth phase, in which wired and wireless networks are truly converged. As we mentioned earlier, when an independent WAC or WAC card is used, wired traffic and wireless traffic is completely separate. As a result, we must separately perform network management, traffic forwarding, port locating, access authentication, and access policy implementation for wired and wireless users. This results in difficult maintenance and management. To try and overcome this, industry vendors started launching their own wired and wireless convergence solutions to implement unified forwarding and management of wired and wireless networks. At Huawei, we developed a native WAC solution to implement true wired and wireless convergence. As you can see in this figure, the Huawei solution no longer uses an independent WAC or an ACU2 card. Instead, the WAC capability is integrated into the switch itself. In this way, the switch not only processes wired packets, but also identifies and processes wireless CAPWAP packets, implementing true wired and wireless convergence. In this figure, we can vividly see the network topology for wired and wireless convergence, in which wired traffic and wireless traffic is centrally managed by switches, and wired and wireless services are uniformly configured and managed on switches. In this way, wired and wireless networks are truly converged, which results in greatly simplified management and reduced network deployment costs. Just now, we looked in detail at the 4 phases of wireless evolution in enterprise campus networks. For more details, take a look at our new book, Campus Network Architectures and Technologies. This book comprehensively describes how to build an ultra-broadband physical network on a campus and also provides detailed suggestions for the planning and design of wired and wireless networks. By now, you may be wondering how campus networks will evolve in the future. It is obvious that wireless networks have brought significant convenience to us all. Looking ahead, fully wireless access of terminals is not only a trend for future campus networks, but also something that all digital transformation pioneers will choose. To keep up with this, Huawei released Cloud Campus 2.0, its latest campus network solution, at the Global Analyst Summit 2020 in May. This solution stands out with intelligent upgrades in connectivity, experience, and O&M, with features known as supercapacity, intelligent experience, and autonomous driving. This figure illustrates the overall architecture of Cloud Campus 2.0. We can see that terminal access has become fully wireless, and multi-GE switches are also used to meet Wi-Fi 6 backhaul and PoE power supply. This means that each user is provided with gigabit bandwidth experience, and ultra-long distance PoE++ power supply is offered to APs and IoT terminals. Cloud Campus 2.0 delivers gigabit bandwidth, 10 millisecond ultra-low latency, lossless roaming, and end-to-end security needed for key office and production applications. It also implements end-to-end automation from network design and network deployment, all the way to service provisioning and network optimization. By deploying Cloud Campus 2.0, organizations, large and small, can build a future-proof campus network featuring supercapacity, intelligent experience, and autonomous driving. In short, Cloud Campus 2.0 is a good fit for enterprises, governments, educational institutions, hospitals, retailers, transportation organizations, and other industry players looking to accelerate their digital transformation. Well, that brings us to the end of today's IP Tech Talk about wired and wireless convergence. Thanks for watching, and see you next time.